So before we can talk about algebra, which is a way of manipulating and working with numbers, we have to first decide what a number is. And here, you're going to have to resist the urge to think of all numbers as being the same as all other numbers. Nothing could be further from the truth. In fact, over the next couple years, you will only deal with a few number types compared to all the different types of numbers that can be discussed and manipulated in algebra. Specifically, and for all of pre-algebra and algebra 1, you will be dealing only with the real numbers. I know what you're thinking. Aren't all numbers real? Well, in fact, all numbers are not real. There is such a thing as imaginary numbers. How cool is that? And they're super easy to work with. Even though they're made up, we can still, using algebra, work with them. But don't worry, that's for later. Right now, we're just going to deal with the real numbers. And a general way of talking about real numbers is real numbers are all the numbers that you can put on a number line. You've already graphed or plotted lots of different numbers on a number line, so that means you already are pretty familiar with working with real numbers. Once you've divided or taken the whole group of all numbers that are called real numbers, we want to break this into two separate groups. There's a group of real numbers called irrational, badly written, there you go, irrational numbers, and another group called rational numbers. So at this level of algebra, we're not really going to worry about sorting irrational numbers, but we can sort, and we care about the sorting of rational numbers. So these can be divided into two groups. The first group is non-integer. So non-integer rational numbers and integer rational numbers. Again, we're not really concerned about sorting non-integer rational numbers into smaller groups, but the integers we can sort into two separate groups. The first would be the negative integers. Resisting the desire to say positive, these are actually the whole numbers. And last, but certainly not least, we're going to leave the negative numbers alone, but we're going to divide the whole numbers into two groups, one containing only the number 0, and the other containing the natural numbers. So now that we've totally sorted all the real numbers out by categories or into subcategories or subgroups, basically sorted them like we would beads of different shapes and different color, let's talk about each one in turn and talk about them using the number line to understand them. And I'm going to move my number line, and I think I'm going to move my number line down here. Don't know why, just kind of like the look of it, I guess. Okay, we're going to start at the bottom and kind of treat this sorting of our number types as a little mini history of math. So when you think about math way, way, way back in the olden days, before any real math had ever been developed, all we really had was a need to count things. So if you had pigs and you wanted to know how many, you would just count them. And then those are the natural numbers. You would naturally count by going 1, 2, 3, on and on and on, till you got to as many pigs as you had. So on the number line, you're used to plotting points like that or putting things like that on the number line. You'd have 1, 2, 3. So we know it's a real number. We know the natural numbers are real numbers because they're easily put on the number line. And they're the first numbers that were ever used, the ones to just count things that we had. Well, at some point, counting becomes harder to write down. You can count to 108 pigs, but if you don't have a way to space the 100, here's your conundrum. Let's put it up here. If you know you have 108 pigs and you count to 108, that looks like 18. You have no way to place a space between the 1 and the 18, 1 meaning 100 and 18. Now, we use a 0 here without ever thinking about it twice, and it just seems so obvious and natural. But for a long time, that was not obvious and natural. 0 was actually discovered. Once 0 was discovered, everything broke loose. All the floodgates. It was so exciting I can't even speak. The floodgates in math broke open once 0 was discovered. It was maybe the most important thing that was ever discovered in mathematics. So 0, we want to ask, is 0 a real number? Well, sure it is, because it's easy to put on the number line. There it is. So if we look at 0 and the natural numbers together, now we're able to talk about them. You have the distinct set of 0, the distinct set of natural numbers, but if you put all of those into one bag, they're a new set called the whole numbers. So 0, 1, 2, 3, on and on and on to infinity are the whole numbers. They're the counting numbers plus 0. Well, it's super easy to see that once we have 0 and the natural numbers, which are actually now called the whole numbers if you take them all together, it doesn't take long to notice that you have a center point where nothing is happening and you build positive toward infinity. But look at all this empty space over here. What could possibly be happening over here? Well, that's where our negative numbers come from. If I take a number to the left of 0, that's exactly the same distance from 0 as 1 is, then I have a negative 1. If I take a number to the left of 0, that is exactly the same distance from 0 as the 2 is, then this must be negative 2, and so on and so on, all the way to negative infinity. Now the number line looks totally different, right? The first number line just had natural numbers, 1, 2, 3. The second number line had whole numbers, which was 0 and the 1, 2, 3. So you have the natural numbers add 0. The next iteration for the number line is integers. We have the positive integers, we have the positive whole numbers or natural numbers, add 0, and we also have all of the negative integers. So the negative integers have another name because they're on the opposite side of 0. So negative 1 is on the opposite side of 0 from positive 1. Negative 2 is on the opposite side of 0. We also call the negative integers the opposites. Okay, our number line is taking shape. And by the way, this would probably be a good time to say I stopped underlining at 3, but this goes all the way to infinity, right? And on this side also goes, well, let's get this. So the natural numbers go all the way to infinity. 0 plus the natural numbers, which is the whole numbers, go all the way to infinity. And then the integers, or the negative integers, go all the way to negative infinity. And in the positive direction, they go all the way to positive infinity. So we're building up our number line to include all the numbers that are contained in the real set of numbers that we're going to work with on a regular basis. So let's move on up. We have from integers, so everything on the number line now is an integer, but if we add to it non-integer rational numbers. So what is a non-integer? Well, that would be numbers that fall not where these numbers that we're used to working with are. They're numbers that fall somewhere in the middle. For example, right here, I could put 1/2 on the number line. This is a fraction because it's not 0, it's not 1, it's halfway in between. I could also put, let's do this one and call it -1.8. Also, another way to write a fraction was as a decimal. It's almost to -2, but bigger than halfway. Let's see, another thing I could choose is I could put, well, let's do 2. Could write a mixed number, 2 3/4. So these are all fractions written in different forms, but they're all numbers that can easily be put on the number line, so we know they're real, but they're not integers. They're not the whole numbers that are easy to count. They're fractions that fall between them. So these numbers, combined with all the numbers we already have, are called rational numbers. So this is a rational. Everything 0 would be a rational number, 1, 2, 3, all the way to infinity, 0 to -1, -2, -3, all the way to infinity. But the rational numbers also include all the numbers in between each of these. Isn't that crazy? It's kind of everything, almost everything, because we still have these irrationals out here to deal with. So these would be the rational numbers all the way from -infinity to +infinity. And it includes all these numbers in between that we're able to actually identify a location. I know that 1/2 is 1/2, and I can put it right here. The problem with an irrational number is irrational numbers are numbers that can't be written like a fraction or a decimal. They fall in between, but they never end, so you can't ever say what they are. Pi, for example, is 3.14 la 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 la, and it goes on to infinity. It's a never-ending decimal number. And so I know that pi is going to be somewhere just past 3, but I can't actually put it in a place because I don't really know what's on this side or this side. So I can sort of position about where it's going to be, but I can't ever just stick it on the number line, because that decimal, every time I think I know where it lives on the decimal line, on the number line, another decimal place comes up, and then I have to fine tune it, and then another decimal place comes up and I have to fine tune it, and another one. And so I never, ever, ever get to settle on a specific place where that number exists. So those are called irrational numbers. Luckily, we don't do a lot with irrational numbers early on. You get a chance to get really good at all the other types of numbers. But still, it's easy to see that 3.14 blah, 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 blah until infinity would fit somewhere on the number line. We just can't say where. So I'm going to put an X here because we can't really say where pi fits. Okay, so that would be an irrational number. That's a lot, but where we've ended up is we are able to say that the real numbers are all the numbers that can be put on the number line, all the way from -infinity to +infinity, and that depending on how they're placed on the number line, we can put them into separate groups. Now, I use this color coding for a specific reason because notice, let's just look at the number 2, for example. So let's say I just look at, I'm going to put a parenthesis around it so I can just look at the number 2. Notice that the number 2 has been underlined in green, which means 2 is a natural number. But 2 is also a whole number. 2 is also an integer. 2 is also a rational number. Wait a minute. Didn't I just say a minute ago that rational numbers are fractions? I did. So is 2 a fraction? Of course it is. We know that if rational numbers are fractions, then 2, because I've broken these into sets, and so I'm saying that 2 is definitely a rational number because it contains the integers. If 2 is an integer, it has to also be a rational number, and that's obvious once I write it out, because I can always write 2 as 2 divided by 1. It's a fraction. It doesn't have to be a fraction that we write as a fraction all the time. Just because we typically don't write the divided by 1 over our integers or our whole numbers, just because we don't do that doesn't mean it's not technically a fraction. And so really, if I'm going to put this pink in properly, I'm going to say that the rational numbers, well, let's go ahead and erase it. I'm sorry. I know you're taking, no, well, we're not going to erase it. We're going to notice that the rational numbers are all the numbers, we'll just keep the squiggles, every single number between infinity and negative infinity can be considered a rational number if it can be specifically placed on the number line. If it can't be specifically placed on the number line, it can only be sort of estimated, the area it might be, if only it would terminate with the end of a decimal somewhere, if it doesn't have an x. The x, remember, just represents the irrational numbers that they're there. 3.14 is somewhere around there, but we can't actually put it on the number line. We can't draw a line like here. I could say, well, this is exactly -1/2. No problem with that. But pi, it's somewhere around 3.14, 1415, it never ends. And so the irrational numbers can't actually be placed on the number line, but it's easy to see that they would be there if only we could, where they'd be, in the vicinity they'd be, if only we could actually place them there. Whoa, I am totally tongue-tied. I imagine you're totally ear-tied. So I'll stop now. Okay, I have one more thing to say. Super important, even though it's a lot of talk and a lot of thinking, that you start wrapping your brain around the types of numbers that we're dealing with in algebra. Each of these number sets is handled differently when you do calculations. They all have special rules that go with them. You can imagine that adding and subtracting whole numbers is totally different than adding and subtracting fractions. So they have special rules that go with them. It's super important that you be able to identify numbers by the set they're in, so you can start to really decide how you want to approach tackling those numbers down and beating them into submission. So turn off this video, go rest up, because the battle begins tomorrow.